Okay. I'm back. Apparently they already found someone, so they canceled the meeting. Unfortunately. Okay. So let's go to the problem list. Let's see if we can find another medium. Alright, square root of x. Return the square root of x rounded down to the nearest integer. The return integer should be non-negative as well. You must not use any built-in exponent function as the operator. For example, do not use pow or star star. Oh, I'm sure people did it anyway. For this particular case, I do know the solution already. So we're gonna say x equals x is less than 0. Then we'll do minus x, x. So we're just gonna flip the sign. I think. To potentially make the problem easier. And then we're going to say let output equals x divided by 2. And we'll return output. We'll just start somewhere in the middle. Actually, I think we want 2 variables here. Left is 0. Right is x divided by 2. So they want it within rounded down to the nearest integer. Rounded down to the nearest integer. Which means we should only consider integers while doing this. So we should do math.for. While left is not equal to right, and then we do left, and if we gotta get the middle. Actually, I guess right should be x const middle. So the idea here is we're basically doing a binary search to find the number that multiplies out to x as close as possible. Want to try this next? Yeah, I can do distribute money to maximum children. Yeah, I can do that next. Just give me a moment. Thanks for sharing the problem, Chris. Okay, cool. So we'll do middle times middle is greater than x. I think we could do like an opt-out. Let's do product equals middle times middle. If product equals x, we'll just return middle. Else, we'll do middle times middle. We do product So if it's too big, then we need to say that the right is equal to middle. If it's too small, then we need to say left equals middle plus 1. Something like this. And yeah, I think we return left. We'll just run it for a few test cases just to see how we did. I imagine that we're probably off by 1 in some cases. Or we don't exit. Okay. So in that case, oh, it's not x. It's be left plus right divided by 2. Take the actual average of the thing we care about. The thing keeping track of where we are in the list. Okay, this time we got an output of 3, we expected 2. So let's think about it. So the input is 8. So we could say x equals 8. And in actuality, yeah, the square root is like some kind of 2 point something. So we should floor that. I wonder if we just always -1 from left? Maybe? I think it's just something we could try really quick. Just to see. And the only reason I'm saying that, basically the idea is pretty much we're always going to be under at the end, I would imagine. Because if we'll always end up with a decimal. And can I even reason this logic? For 8 is fine. 4 we have a cheat. We have a breakout early. I think of like an edge case in which we might end up over. Maybe 10. I don't know. Let's just submit it. Output -1. Expected 0. The input is 0. Okay, so we don't go through this at all. We can have like an escape hatch here. Handle that edge case. One also doesn't go in. So in this case, left is 0, right would be 1. We should go into here. The middle of 0 and 1 is 0.5. Okay, it's not that easy then. Okay, I have another idea then. What else do we do to reach that consideration? Okay, so my idea is if left times left is greater than x, then we return left, otherwise return left -1. Basically the idea is if we went over, then the number we have is already floored, but if we're under, then the number we have isn't. Because in the case of here, we end up with 3. That's what I think will get us there. Wow. We have 3. 3 times 3 is... Oh. Hopefully it's just backwards. Okay. We can actually get rid of this escape hatch now. Okay. This is like another escape hatch we can get rid of, but it's fine. Let's look at the better solutions. I swear that they probably just returned math POW or math square root. And they didn't. They have pretty much the same code we have, except just less, just shorter. They also did the same thing. What are some of the slower solutions used? Okay, I guess just because they did multiplication multiple times. Okay, cool. That'll be that. Okay, Chris. I will check out your problem. Give me a moment. Interesting. Yeah, there we go. Okay. Okay. So we have an easy problem here. Let's take a look at what we're given here. You're given an integer, money. So money is an integer, yes. Denoting the amount of money in dollars that you have, and another integer denoting the number of children that you must distribute the money to. You have to distribute the money according to the following rules. All money must be distributed. Everyone must receive at least $1, and no one receives $4. Return the maximum number of children who receive exactly... I guess this means no one receives exactly $4. Return the maximum number of children who receive exactly $8 if you distribute the money according to the rules. If there's no way to distribute the money, return -1. $20, 3 children, output is 1. The maximum number of children is $8 will be 1. One of the ways to distribute the money is 893. It can be proven that no distribution exists such that the number of children getting $8 is greater than 1. And then we can't do, for this solution, we can't do 8, 8, and 4 because we can't do 4. And they have to receive exactly $8. 16, 16 would be, and there's 2 children, that would be 2. Okay. And then everyone has to receive at least $1. Okay. All money must be distributed. Okay. Let's think through this then, because a bunch of random rules here. I will say that I'm surprised that it's easy, but I think once you know the algorithm, it probably becomes very easy. The money is always between 1 and 200, and the children is 2 to 30. So those are the constraints. So I think probably want to consider like a naive solution. And I'm also thinking that we kind of have to be greedy here. I'm also thinking potentially there's a recursion aspect to this. So lots of things. Do I have an interview soon? I had an interview that was set for 15 minutes ago. But they literally canceled this morning. I emailed them. I was like, hey, what happened? Did you know, do you want to reschedule? And like, actually, we wanted to hire 2 people. We already hired them. So I didn't even get to, you know, put my case to them. So unlucky. Bad timing, I guess. But like I applied to 16 jobs yesterday. One of them was that one. So hopefully something happens. Somebody gets back to me. Yeah, it is big oof. But just gotta keep pushing. I'm also trying other avenues. I created a Preply account. Maybe I can tutor people. I do like teaching. So something to consider. In the meantime. But back to your problem. This seems like it has the potential to be a simple division and subtraction. Like my intuition tells me that this could probably do, and we could probably do this in constant time. No looping required. So the first step is make sure everyone gets $1. So basically the money minus equals children. To me, that's the simple approach. And then we got to be greedy. How many children can get $8? And so given that we've already given everyone $1, the count would be the floor of money divided by children. But we're basically done here. We're basically done, but we gotta consider this last one, that nobody receives $4. And basically the way we could detect that is if we basically after we were so greedy, we need to figure out the money that we have left and how we can distribute it to the children. Given that the rest of the children only have $1 already. So I think money at the very end, we're probably gonna have like some kind of condition that makes it so that it's either count or count minus 1. But we need to detect money. But then we also, if the money can't be distributed, we get -1. which is strange. Basically, if there's, I guess, 0 children, the count is 0, then we give -1. Children, no, count times 7. So this will be how much money we have left after we've given those children, so with this greedy algorithm, $8 each. And then we have to do this detection. Basically, like, to me, I don't see any reason why, like, if there's at least a child, if there's more than one child, then we can guarantee that they won't get. Oh, but then I guess then the question is, what if there's so much money? There's so much money that nobody gets $8. All the money must be distributed. That's another really important condition. Hey him, welcome back. Thanks for the encouragement. All money must be distributed. Alright, we'll have to think of that edge case. So the edge case is lots of children, or lots of money. Return the maximum number of children who receive exactly $8 if you distribute the money according to the... If there's no way to distribute the money, return -1. This part makes no sense to me. If there's no way to distribute the money, so it's basically asking you to never return 0. It's either return -1 or a positive number. So how many children get $8? Like, so one of the things at the end, if because there's nothing stopping a child from getting like $1 million, right? So something to the effect of, if count is less than children, or sorry, if count equals children, and there's if children equals 1, I feel like there's gonna be like edge cases here, and I'm just trying to figure out what those edge cases are. Month for some reason. All money must be distributed. All right, let's deal with all money must be distributed. Basically the idea is if there's still money left over at the end, then we'll return count -1. Basically the idea here is our child, and we'll do, this is dirty, but if there's any money left over, then we just gotta take all the money and just give it to one of the children. And every other child will still get $8 except for this last child. That's the idea. And for this one, we need to look at the remaining money. I think there's also just return count. I think we've considered lots of money at this point. Nobody receives $4. So basically, if the children minus count is greater than 1, or the money is not equal to 3. Basically saying there are children to distribute the money to. Actually, there are no children to distribute the money to. Would be children minus count equals 1. There is only one child to distribute the remaining money. So if there's only one child to distribute the remaining money, and the remaining money is $3, then we actually return count -2, because not only can this child who's getting 4 not receive that amount, the child before them, we need to adjust the amount of money they're getting in order to give this child who's getting 4 the correct amount. So, and then if that's 0, then it's -1. I'll put one child left. If there's one child left and the amount of money is $3, then we need to redistribute the money between the last 2 children. Which actually it's just count -1, right? Because we've already counted these 2 children who have $8 as having counted. It's this last child who we need to. So we're removing the second to last child. Something like that. So all money must be distributed, that's this condition. Everyone must receive $1, that's here. Nobody receives $4, that's this condition. And then I guess this very last case, if we return 0, we should return -1. If either this is correct or I don't understand the question. Okay, maybe I don't understand the question. Okay, so we have 20 monies, 3 children. The output is Wait, what am I outputting? What am I outputting? Maximum number of children who receive exactly $8. Okay, output 4. Should have gotten 1. Okay. Oh, this is probably... How am I possibly gonna be outputting 4? I guess one thing I didn't consider for the count, max dot, not dot max or min. So, thinking about this, money is 20, children is 3. It should be like 2 point something, which would become 2. This would be 2. Do we need this? Two is the count. Like, am I really bad at math? Wait, what am I doing? Okay. I don't know why I did that. Mathematic. Okay, so thinking about this becomes 17. And then this will be 17 divided by 7 is 2 point something, which becomes 2. Money minus equals count times 7, which gives us 14. 17 minus 14 is 3. So money is $3. Then we will detect this edge case. And then we'll go down this one and make it 1. Okay. Okay, I just put the wrong variable there. The wrong value there. We can submit it. I'll put -2. So if the money is not enough, so we're going down one of these, probably this one. I think to make things easier, I'm gonna do function intermediate and just simplify this. And then in here, we'll do return intermediate. Same arguments. Intermediate, money, children. And we'll do math.max of -1, -1. That way we don't have to write this expression everywhere. We're able to remove it from a lot of places as well. We're going to run it against the 2 test cases just to make sure. And then we're going to submit it. Expected 0. Wait, what am I? The maximum number of children to receive exactly $8. Okay, so I am not understanding this question correctly. Let's go back to my submission. It should be 0. I got -1. Okay. You can give 1 to each of the 2 children. Yeah. Give 1 to each of the 2 children, return 0. But no one gets 8, yeah. Okay, I thought that at least one child had to get 8 in order to trigger. So the main thing is that no one gets 4. Okay, complicates things a little bit. Okay, so we start off by giving people money. We'll end up with 0 money, it'd be 0, count 0. If there's 1 child left, then there's 3 monies. Okay, and then we're doing this or -1, which is 0. This one I feel like this is probably the most complicated condition. Nobody receives $4 because you have a choice of not giving people $4. So you basically need to be able to detect there's the case where there's enough children to distribute so that they don't get $4. But then there's also the case in which I guess there's 1 child and there's only $4. So if there's 1 child left and there's money to distribute, but the other thing is if there's 1 child and the count and the okay, so children equals 1. If there's 1 child in general and money equals 3, then we return -1. Something like that. But it didn't run last time. Submit. Output is -1, expected 0. Okay, let's run that then. So every child gets $1. The count is 0. There is 1 child left. There's 2 children left, so we don't go down this one. But there is money left over. Probably this. Maybe we don't need this anymore. I feel like that's cheating now. Okay, in that case, we could just bring this code back in. Alright, let's run it. Just a minute. Oh, I'm still getting -1. For this one, there's not enough money. So the money ends up being negative, which is interesting because that could affect the count if there's so many children and no money. That could affect the count. So we're gonna have to do this to handle the cases in which there's way more money than... Yeah, we keep going. No giving up. So thinking about this, one child left. We don't go through this because we have 2 children left. There's 1 child in general, but okay, we won't go down this because we're doing this max now. I think money was -1, which is causing us to go down into this route. Let's just run it to see if the base tests pass. We could submit it. Still -1. Okay. Let's like start plugging stuff in. 1, 2. So this will be money minus children. So money is now 0. The count will be money divided by 7, which is 0. This is still 0. Children minus count, which is going to be 2 minus 0. This will be false, which means we don't even check the money amount. This will be false because children is 2. And then money is 0. Money is... Just put it here for now. We're gonna go false there. All money must be distributed. The money should be 0. And then we return count. I would expect a -1. Oh, because every child needs to get $1. Ooh, that's a requirement. Everyone must... Okay. We don't need that, Max. We need to do if children is greater than money. Return -1. And then the rule that we're satisfying here is everyone must receive at least $1. Cool. Let's run it for the base cases. And we'll submit it since it passes. Okay, there's more. Alright, just thinking about this. I feel like it should be 1, but we got 0. So let's see if we can figure out why we got 0. So the values here are going to be 10 and 2. Is children greater than money? I'm just gonna reverse this just so that the variable names align with each other. If there's not enough money for every child, return -1. Money is 10, which is not less than children, so we continue. Next, we give each child $1. So money is, we're gonna go back to minus equals. Money will become 8. And then count will be 1, because 8 divided by 7 is, and flooring it is 1. So then the money becomes 8 minus 7, which would be changing this to be 1. Okay, so if there's one child left, is there a child left? Children is 2 minus count, which is 1, gives us 1. There is one child left. Is the money equal to 3? Money is 1, so it's not. We continue, so this is false. Actually, this was true for this. Is there generally one child? No, that's false. And then finally, is there money left over? There is money left over, but I guess this is a little bit more complicated. If there's money left over and there's not one child left, then we gotta say, okay, well, one of the children gets screwed over and they get the minus, they get excluded from this because we want to max it out. This last child actually doesn't get gypped because they get all the money. They get the rest of the money. Alright, we'll run it. I'll submit it since they passed. Oh, there's more. Okay. Expected 1, which I understand. I agree, it should be 1. 11 and 3. Is money less than? No. Money minus children, so money becomes 8. The count will be money divided by 7, which is 1, which is still 1. Is there one child left? Count is 1. Now there's 2 children left, so this is false, which means we don't consider this. Is there one child in general? No, that's false. And then... okay. We could say... more children equals... children... it's gonna be... children is greater than count. If there's more children... no more children. So if children is equal to count, if there's money left over and there's no more children, then we have to give all the rest of the money to one of the children who did get 8, and therefore we have to decrement the count. Let's run it again. Let's submit it. We got 3 somehow. Let's run it. Let us run it. 23, 2. Everyone must receive $1. 23 less than 2, it's not, so we go over that. Money minus children, so that becomes 21. And the count becomes money divided by 2. Or sorry, money divided by 7, which is 3. And that seems like a problem. Seems like a problem. Maybe, am I doing the math wrong? 23. Yeah, I am doing the math wrong. This was 23. There's 2 children. 21. This becomes 23. Yeah, I'm doing... This got too big. So we do need that somewhere at least. So that brings us down to 2. This would be 14 minus 21 is 7. One child left. There is not one child left. There's no children left, so we don't do this. If there's one child in general, that's not true either. And then there's no more children, which there's not. 2 is 2, and there's money left over. Then we have to decrement. I think we can get rid of this. So ultimately the issue was this count was exceeding the number of children and probably giving us a negative number at some point and messing things up. So let's run it against the base test cases. And let's submit it. Alright, we finally did it. The only question at this point is, can it be improved? Everyone gets at least $1. Make sure everyone gets $1. Give everyone $8 that you can, and then figure out at the very end who you can't give that money to. Okay. There's nothing, it's, you know, it's constant time. Doesn't matter what the value is here. This all runs in constant time, so there's no real way to optimize in terms of complexity. So I'm just curious what the solution of others were. How about this? I'll try it in a second. Let me see what other people did. Ooh. This is clean. Okay, so they give $1 to each child. If there's not enough money, then they return -1. Then they do they see if there's enough money for every child and that the money is evenly divisible by all the children. If that's the case, then we just say children. Very easy. If the amount of money for the children... Okay, interesting. So if there's enough money for children -1, This one's a little harder to reason though. I gotta stare at it for a little bit. Because yeah, this evaluation can get kind of out of hand. Oh, what you floor it, money divided by. And then money mod 7 is 3. Pretty much. But like, what if there's a lot of money? I almost wonder if this one, how necessary this one is. It's so specific. But I guess you do need it. You just need to handle this one edge case of, okay, is there enough money for everyone but one child? And then that child doesn't get, it's basically, it's the edge case of there's one child left and that child gets $3. If there's one child left and that child gets $3, then we actually have to remove children too, 2 children. One to account for the one who was originally getting 3 and one to help to distribute the money out. And then there's this one. This is easy. This is easy. It's easy, but in my opinion, it's easy to, in terms of complexity. It's hard in terms of understanding the problem. So like, yeah, the description is like, it has all these different rules. All money must be distributed. Everyone receives $1. Nobody receives $4. How many children get $8? Return -1. There's all these different conditions. Yeah, implementation is hard. So like, I had to put comments everywhere. I had all these different checks and conditions. So yeah, this is really clean. Wait, why can't I click on it? This is a clean solution. And if you just like kind of know the math, then yeah, you could just write it. This one, they kind of, there's no like clean, really clean, simple way to write this. Like, even though this is clean, it's just really hard to reason. It's really hard to say, why did you write this line? Why did you write this line? More variables or comments might be helpful here. Like caching this value might be nice. Could be something to consider. Caching this value could be nice. Something else you could consider. Yeah, because you do this math floor divide 7 so many times. They probably could have gotten 0 milliseconds if they did that. Maybe. But yeah, that'll be that. I'll do your next problem, Chris. Ooh. Chess. Oh, this is a medium. Okay, this is interesting. I have written some chess algorithms. Okay, there's a one indexed, a single dimension containing 3 pieces. You're given 6 integers, A, B, C, D, E, F. A, B denotes the position of the white rook. Okay. So AB equals white rook. CD equals white bishop. EF equals black queen. And given that you can only move the white pieces, return the minimum number of moves required to capture the black queen. Note that rooks can move any number of, yes. Cannot jump over pieces, yes. Bishops can move any number of squares diagonally, can't jump over, yes. A rook or bishop can capture the queen if it's located in a square that it can move to, yes. The queen does not move. Six integers denotes you can only move white pieces. Okay, the minimum number of moves. So it's always going to be at least 1, the output. So queen doesn't move. That makes things a lot easier. And I think in actuality, we're gonna return 1 or 2. Okay. So my idea is see if the bishop can capture in 1 move. Then see if the rook can capture in 1 move. Else, return true. So return 2. The base case is 2, because as long as there's a rook on the board, you're gonna be able to capture the queen in 2 moves. The only edge cases we need to figure out is, can one of these other pieces capture the queen in 1 move? And it doesn't really matter which one we do, really. So see if the bishop can capture in 1 move. How do we do that? Basically, we could be a little lazy here. So this is basically accounting for the diagonals of the bishop. We don't need to really worry about like an array out of bounds. But I mean, we should consider potentially not overdoing the iteration. But I'm fine with overdoing the iteration for now. And we probably want to do both diagonals of the bishop at once to keep things simple. We can actually be very lazy here. I wanna consider like we could write something to where we just don't care where the bishop is, and then we can improve later once we have an algorithm that works. And then we need to worry about optimization, then we'll do that later. So let's be very lazy, and basically we're gonna do the diagonals of the bishop. So we're gonna, for example, do the bishop is C and D. So in order to kind of simulate doing longest common prefix. All right, nice. I might have already done that. I did already do that. I think I have a video on it too. I could go over the solution later if you want, after you figure it out. But C plus I equals, yeah, go for it. Was it easy for me? Yeah, I would say. Let me longest common prefix. I don't want to open it. I want to try to remember what it was even trying to do. Oh, it was an array of strings, and you were trying to go through all of the strings and see which of those strings, or for each of the strings, which one. Sorry, I'm saying like code stuff, but you want to see how much characters of each string match and figure out what the max is. It's kind of funny because like I kind of can't talk in code. So sorry if that gave you a hint. I was just trying to remember the problem. But yeah, I mean, there's usually with these easier solutions, brute force is pretty applicable. It's hard to do better than brute force for easy. Sorry if that's a hint, but it is easy to implement. But yeah, we're looking at the white bishop, and we're gonna see if it lines up with the queen diagonally. So the queen is at E, and D plus I equals F. Then we'll return 1. So let's just try to comment this a little bit. We'll say like bishop X equals queen X. Let's just call it what it is, I think. A is rook X, rook Y, bishop bishop Y, queen X, queen Y. And just for even more readability, we'll just new line these a few, and then we'll do bishop X plus I, bishop Y, and then we'll do queen X, queen Y. Self-documenting code. But we also, so this does one diagonal, which, thinking about it, it's gonna be, I can't really describe it. But in order to do the other diagonal, I guess we minus one of the y's and we plus the other one. So like in theory, if we were to think about it more of a graph, this would be starting at -8 going till +8, and this will be +8. No, this would be -8 going to +8, and then the y. For the x, it's -8 to +8. For the y, it's -8 to +8. But for this y, it's +8 to -8. So that should get us both diagonals. So that's the bishop. We'll do the same thing. Pretty much the exact same logic here. I is -8. I is less than 8. I plus plus. And then it's very similar. Except it's going to be rook. And we don't apply y for one of the coordinates, and we don't apply x for the other. And so This will be 0 the whole time, and this will be 0 the whole time. And so we're basically just like, for the entire x is the queen there, for the entire y is the queen there. Excuse me. And we'll put that here. Otherwise, we return 2. Right, and we don't need that comment. It's now obvious. And I guess I'll put rook x, y, bishop x, bishop y, queen x, queen y. Okay, let's try it. I think that it'll be slow, but it should work. Or not. Okay. Let's see if we can visualize this. So I said we could do it in 1, but it should be 2. Oh. Okay, here's an edge case. Alright, there's an edge case. The edge case here is the rook is blocking the bishop. And similarly, the bishop is blocking the rook. So the rule that we missed is pieces can't jump over other pieces. Oops. Okay, in that case, we gotta do a many for loops, which we could probably simplify a little bit. Just to see if we could think of a way. Okay, yeah, we might need for loops like crazy. I guess we'll be a little bit more respectful. Are we? I don't know. No, we have to be respectful. I equals bishop x. Okay, so it's gonna be x is bishop x. X is greater than or equal to 0. X minus minus. Once we see a pattern developing here, we'll probably try to reduce the amount of code we have, but I don't know about optimizing it. So one thing we can do is if we can say const piece equals, and we'll say const get piece equals xy, and then we'll say if x equals rook x and y equals rook y, return rook. If x equals bishop x and y equals bishop y, return bishop. If x equals queen x and y equals queen y, return queen, return empty. Okay. Just create a little helper function. So we'll do get piece, and we'll do x, bishop, y, I guess we have to do I. I equals 0. We want to slowly move up and to the left for the bishop. I equals 1. Or sorry, I equals 1. Wow, I is less than bishop x. Fine, let's call it x. But what if it's the y that's important? Basically, we don't want to go out of bounds. And we're going to call it y. I plus plus. And basically, this will be plus the bishop x plus I, bishop plus I. I'll say if piece equals queen, return 1. Else if piece is not blank, great. Something like this. So ideally we would write a function that like takes in a whole bunch of arguments and does all of this stuff for us. So something where I could say like if check if capper queen max is do count, and then we'll do index, and then we'll return x bishop x, y is bishop y, plus index plus index, and then we'll create a function that takes mount and call back and does all of this. count. Const coordinate equals callback I, and that'll be coordinate dot x coordinate dot y. Okay, so we should be able to simplify all of this and have this if return 1. So this will be, so we're trying to figure out how, sorry, these should be minus and minus. So this is a bishop go up left. And we'll do, just to simplify this, we'll do this. We'll do an array. It simplifies it, but it's not optimal. Again, this is bishop up left. And we're only saying it's up left because it's negative index. Then we'll do bishop up right. In order to go up right, there's probably a way to do this so that you don't have to iterate. Now that I think about it. Okay. Let me put this code somewhere else. Let's see if I can explore this idea of doing this in like big O1. So, if, okay, so const can bishop capture queen. The bishop would capture the queen if the queen x minus bishop x equals queen y minus bishop y. So let's think about that. So basically what I'm saying is the queen is capturable here. So the difference between these two, needs to be equal. If you go too far up and not far enough over, then you're not on the same diagonal. So okay, if bishop can capture queen, return 1. Return 2 is our base case. We've already discussed this. If const can rook capture queen, the rook can capture the queen if the queen x equals the rook x, or the queen y equals queen y. But then there's the edge case. Can bishop capture rook? And it's very similar logic here. The rook x and the rook y should be y, capital. And then we gotta say const queen distance. This is a little complicated, I guess, because we gotta see if the queen is in the same direction. Okay. Const dx const dy capture the queen if dx is dy. I'll call it qdx qdy, and then I'll call const rdx const rdy rdx rdy. Const is same direction if math.sign of qdx equals math.sign rdx and math.sign qdy equals math.sign rdy. So basically, are the queen and the rook in the same direction? So we can capture the queen, the bishop can capture the queen as long as it can capture the queen. It can't capture the rook, or they're not the same direction, or okay, qdx times qdx is less than rdx times rdx. We already know that rdx is the same as rdy at this point, so we just multiply them both out. So basically the question we're answering here, can we do this bishop capture in one move? I'm definitely getting rid of this old code. We're never gonna use it. So does qdx qdy, rdx, rdy. Can bishop capture rook? The bishop could capture the rook if rdx equals rdy. Are the queen and the rook in the same direction? Sine of qdx equals rdx. Sine of qdy equals rdy. So we can capture the queen if we can capture the queen, and we can't capture the rook, or the two pieces are not in the same direction, or the queen is closer than the rook. That is the logic. And then the next thing is to do it all over again except for the rook. So I'm gonna do const handle bishop. I'm gonna move all this logic into there. Same arguments. I'm doing this just so I can reuse variables. Okay. Okay, so I don't think we need the differential anymore. We might. Rook X, Rook Y. This would be called handle rook. Rook X, Rook Y. Can rook capture queen? The rook can capture the queen if the rook X equals the queen X, or the rook Y equals the queen Y. And then similarly, can rook capture? We go as long as it takes. Yes. We're on our way to a solution though, a big O1 solution. Yeah, for sure. Rook X equals, and rook capture bishop. And try to have the code be self-documenting. Bishop X or rook Y equals bishop Y. So we first determine if they're capturable. They're capturable if they're in the same rank or file. And then are they in the same direction? Maybe we do need dx and dy. The only problem is that they could be 0. This should be b dx, b dy. And ultimately, the only reason this code doesn't end up working is because I copy-pasted something incorrectly. Can rook capture bishop is same direction. I think we gotta do QDX and QDX equals RDX, or QDY and actually, is it that simple? Basically, if QDX is in some direction and RDX is in that same direction, or QDY is in some direction and BDY BDX is in that same direction. So can rook capture queen? Can rook capture bishop? Is same direction. This time is a little bit more complicated. I guess we could technically get away with just doing a square. This is BDX. Wait, no, yeah. Plus BDY. Let me just new line this. And new line this. I'm gonna do this too, is closer. Queen is closer. I'll do the same thing here. This right here is very lazy, very lazy. I just don't want to figure out which of these have a value. I could do QDX, then QDX, otherwise QDY. And then do map.apps. Am I using these anywhere else? I am. So see if the queen is less than math.apps. I have BDX, BDY. Okay, no longer lazy. Let's just run it. Actually, did we call the function? We didn't even call it. Handle, rook. Same arguments. Run. Oh, syntax error. Run it. DX is not defined. UDX, QDY. Can bishop capture queen? Yeah. Okay, we passed those test cases. Let's see if there's test cases we don't pass. Submit it. So we expected 2, but we got 1. We'll do a bunch of logs. Go down here, do a similar log. Cool, we'll run it. So we said that we could do it in 1 move, but we're supposed to be able to do it in 2. Where did this come from? Interesting. Submit it. Let's see what response we get. So what is 1 expected 2, which means that we are detecting that the rook can capture the queen. So maybe one thing that we can do is go to LeetCode to visualize. And how do I board editor? All right, let's take a look. Is there a quick way to pull these off? No. What's this do? Awesome. All right. Okay, so we start with the white rook. The white rook is at 1-1. And then we do the bishop, which is at 1-4. White bishop. 1, 2, 3, 4. And then the queen is at 1-8. So yeah, we can see we are potentially detecting the rook to take the queen. So we're not detecting something properly with the collision detection. So rook can capture queen, that is true. Rook can capture bishop, which is also true. Are they in the same direction is false. That should be true. So let's take another look. QDX, QDX, BDX, QDY, QDY, BDY. So I don't know if it's like a parentheses issue. Doubt it, but I'm going to add parentheses anyway. So the QDX is queen x minus rook x. Just for reference, we did it like this, so that the piece we cared about was always on the right. That's important. Okay, let's submit it again. Okay, is this the same problem? It's not. Okay, so let's set it up. We have a white rook at 0, 1, 2, 3, 4, 0, 1, 2, 3. Excuse me. We have a white bishop at 3, 4. Where do we have it now? 0, 1, 2, 3, 0, 1, 2, 3, 4. Then we have the queen at 2, 5. 0, 1, 2, 0, 1, 2, 3, 4, 5. So we're supposed to say, I have to be doing something wrong here, right? Oh, we're saying it takes 2 moves. So we're not detecting that the bishop can capture the queen. Hand on bishop. Queen X minus bishop X. So X, X, Y, X, Y, X, Y, X, Y, X, Y. Can bishop capture queen? So, oh, okay. We gotta do this. Basically, it doesn't matter if it's negative or positive. Can we do it sooner though? Yeah, we can't do it here because we need to know the sign to know the direction. Okay. Cool. Got another. It's the same one. It's the same one. Except this time, that's not how you do it. Cool. Wow. We did it. Let's remove the console logs. Since console logs are slow, we'll submit it. Oh, killing it. 100% better than everyone. Yeah, easy clap for sure. Even the memory is pretty good. I'm sure there's ways to optimize it. There's like how to be micro optimizations. The memory is linear and the runtime is linear. I am curious to see if there's better math solutions than the one. Wow. They just completely golfed. They golfed very hard here. I'm curious if any of the solutions have a loop. I'm gonna ramp it up a bit. Let me see what time it is. 1:21. Let me just look at a few more solutions. I'm curious if anyone did a loop. Let's look at the slowest solutions. Oh. Oh, wow. They created a whole chessboard. Put in what kind of moves these characters can make, these pieces can make. Ooh. Is visible by rook. Is visible by bishop. If is visible or is visible. Wow. Yeah. Interesting. They even have an inbounds. Wow. Oh, this one's very interesting. That's what I wanted to see. Oh wow, are people cheating? It's like the same code, except for whatever reason they use a uint8 rather than an array. And oh, it has the same exact comment. Interesting. I wonder if ChatGPT gives this answer or something. Another one. It still runs pretty fast, despite it having all this extra code. Wow, what is everyone cheat? You gotta hit like the 2 milliseconds for people to, or the 3 milliseconds for people to potentially stop cheating. Oh, I can't believe people wrote this. That's crazy. Okay, that's that. Oh, you have another one for me. Medium. Wait, close this, close this, close this. Okay. Alright, Alice and Bob continue their games with stones. There is a row of n stones, and each stone has an associated value. You are given an integer array stones, and stone sub I is the value of the I stone. Alice and Bob take turns, with Alice starting first. On each turn, the player may remove any stone from stones. The player who removes a stone loses if the sum of the values of all removed stones is divisible by 3. Bob will win automatically if there are no remaining stones, even if it's Alice's turn. Assuming both players play optimally, return true if Alice wins, false if Bob wins. There's a row of n stones. Each stone has a value. You are given an integer array stones, where stone sub I is the value of the ith stone. Okay. Alice can remove either stone, but Bob removes the remaining stone. The sum of the removed stones divided by 3, therefore Bob loses. I think like the challenge here is trying to determine what is playing optimally. Alice takes turns, starting first. On each turn, the player may remove any stone from stones. The player who removes a stone loses if the sum of the value of all removed stones is divisible by 3. This requires some level of understanding of like min-maxing. So I want to just talk through the potential naive solution, which would be some kind of solution that uses recursion. Excuse me. And recursively removes certain stones from the collection. So let me make a note. Alice and Bob take turns on each. So I'm gonna do const Alice equals return true if Alice wins. Const Bob equals false. And then whose turn is it? The other solution I kind of think is going to be some kind of a tree. Alice and Bob take turns with Alice starting first. On each turn, the player may remove player who Alice starting first, so Alice is first. Great. So I think my first instinct is to do like stones.map stone with index. I think we gotta keep track of the sum so far, which is gonna be 0 by default. And it's supposed to return the winner. So we'll do const results. We return who wins. There's no remaining stones. Bob will win automatically if there's no stones. Bob will win if there are no stones remaining, even if it's Alice's turn. Okay, so the other thing is if stones.length return Bob. Hey, how's it going? I'm trying to decipher your name. I'll call you Manic for now, but how's it going, Manic? I'm doing alright. Just solving some LeetCode. We're doing a medium challenge of the stone game, which seems like a recursion problem, but I could be wrong. So at this point, it's representing, I think we have to do something like if stone plus sum mod 3 equals 0, and we return not turn is the winner. Otherwise we keep going. Oh, but we can't. Yeah, but no, we're good, we're good, we're good. And then we do return stone game IX and the stones sum plus stone not turn. Bob will win if there are no remaining stones. Divisible by 3. Assuming both players play optimally, return true if Alice wins and false if Bob wins. Alice goes first. And then here it's going to be return results dot includes turn. And then here stones needs to decrement by, it needs to remove the element. They need to do like stones dot slice 0 dot splice index 1. So we make a clone, remove the stone we took, change whose turn it is, and add the sum to the stone. I'm gonna run this. I think if we're gonna run into an issue here, it's probably gonna be a runtime issue. Like a speed, performance. Not a error. Okay, so Alice goes, then Bob goes. When Bob goes, it should, Bob is false. Okay. The output is false. I returned false. Bob is false. So I'm trying to think why that would be the case. So stones, some turn. Stones has an item. We'll go through each of the stones. Stone plus sum mod 3. We return person whose turn it's not. Let me just do a log here. Just to make sure we're actually going down that bit of code. We're not calling that. So let's do this. We'll do stones, stone, sum, index, turn. Interesting. Why are we not logging? Oh my gosh. What am I doing? This should be stone. No R, it's stone. Run it. Output should be true, expected false. It should be false because Bob wins. Because Alice instantly takes the last stone. So if we run through it, The results, map stones, it'll be 0 plus 2 is 2, so we'll instead rely on the game continuing. We'll remove that stone, say it's 2, say that it's Bob's turn. But when we go in here, we should get false. So I'm gonna do a console log of result here. With an S. Stones, sum, turn, result. Okay, let's see if we can understand this. How does the sum get to 4 ever? How do we even call this log as many times as we do? It seems like stones always... Oh, okay. Let's do that, which means we'll no longer have stones and turns. Or, yeah, well, let's run that. This is very curious. Why is it not splicing? Eventually we hit 6, and that's when we're exiting. So let's console log stones index. Yeah, why isn't it removing the 2? Am I like completely not remembering what splice does? Oh my gosh. No, wait, yeah. Why isn't splice working? Index? The number of elements to remove? Stones dot slice index +1. Try that. 2, 1 becomes just 1. 1 becomes 2, 1 becomes 2. Okay. Just do a different way of moving stones, I guess. Okay, yeah. So this should be returning true. So this should be returning not turn. Okay, so this should return true, that's right. This should return true, that's right. But this one returns false, false. Oh. So this is the result of this. It's Bob's turn, but Alice wins because Bob's taking the stone. This one, Alice wins because Bob's taking the stone. So Bob is false. Maybe this logic's wrong then, I guess. Because the true makes sense. And the true makes sense. But then the turn is false. Which would keep it false. Okay, yeah, this is definitely the wrong logic. If it includes their turn, then whoever's turn it is will be the winner. Otherwise, it's whose turn it isn't is the winner. Because they're going to prioritize the thing that makes them win. Cool. Let's run it again. Never mind, let's submit it. Hopefully it's not a time issue. No, so there's an optimization. Okay, so one optimization that comes to mind. I gotta see. Are they random or are they unique? I'm just trying to see if there's any duplicates. Alright, so one thing that comes to mind is adding some kind of a cache. Essentially some kind of idea of if I've already taken the stones in a certain order, I shouldn't do it again. We do like const result equals return result. Just don't know how much it helps. But we could do taken and cache. And gotta do a key somehow. And we gotta say cache subkey equals. I'll do this first. And I'll say if cache subkey return cache subkey. Do that. Then the only thing to really figure out is how to do the cache, or how to determine the key. It's not really the what's taken, it's what's remaining. I feel like. But like if we did stones dot join comma, we don't even need that. If the same stones are remaining from one run to another run, then we know the answer already. In theory, but this is expensive. It still takes too long though. We do use the cache, at least. I use the cache a lot. Too much recursion. Alright, so then the question becomes, how do we trim the tree? Thinking mod 3. And whether certain moves are forced. Okay. That makes me think you don't want to lose. Okay, I need to walk away for a bit. My dog needs to be walked. So I'll be back in like 15 minutes. But I'll leave the stream running, I think. I don't know what I'm gonna do. Let me add some text or something. Censor all this. Let me tell people when I'll be back too. Okay. No, I'll keep going. It's not me who's giving up. I just gotta walk my dog. I'll be right back. All right. I'm back early, but I'm heating up some food too, so I will probably eat at some point. Oh no. All right, so trying to think of what you said. I think in mod 3, if certain moves are forced. Pretty much we're asking if there's some way to not call this as many times as we are. I imagine that the caching is not really helping us, so I'm going to remove it for now. I think in mod 3, are there any forcing moves? That is a good question. So I guess one thing that kind of comes to mind is this idea that taking certain stones might not matter. So for example, depending on... Okay, so essentially the idea that taking the stone that's 4 will yield you the same game end state as taking a stone that's 6 probably. There's some general idea that I have is that taking certain stones in certain scenarios will have the same end state because they offset you by 3 and kind of leave you off where you started. So in that regard, yeah, maybe caching is not enough. I'll get rid of all this idea of caching. So I have a different idea for caching, I guess. This idea that which moduluses have we handled so far, essentially, and it'll be nothing. And so key equals stone dot sum mod 3. At the key sum, what am I doing? Key. The parentheses run that, and then we'll see if handle sub key with key in, then we'll return handle sub key. Otherwise we'll say wait, there's no cache variable anymore. Otherwise here we'll return result, and we'll also say handled sub key equals result. That's the idea I have. We'll try it. Okay, submit it. No, how is it still slow? Like, I feel like this should, like, a third, like, reduce the problem by a third. I'm a little surprised. Wait, does in not do what I think it does? Let me do that. I do use the cache a lot. Hmm. I wish I had some sense of how much better I was doing than before. I guess I'm getting to test 32. What test do I get to right now? Same test. We could do this. We could just say key equals 0, or return turn, return handled. It's not gonna bring us to success, but it's less calculations. Alright, this one seems like quite a doozy. I am considering using a hint. Because yeah, other than 1/3ing the problem. So part of me wonders if I could possibly even do this without any kind of recursion. Or if I can like drastically simplify the number of stones I'm working with. Because in reality, we can do stone turn sum. Stones is an argument here. Like maybe there's a way to simplify this where the input is additional pipes. The input, we would map it to item. item mod 3, right, to simplify it. But is there something more we can do? Like, can we remove certain stones? Is there a way that we could say, oh, this doesn't matter. Now that we've simplified the problem, in reality we just have zeros, ones, and twos. I think what I'm gonna do here is basically anything that becomes 0 will go back to being a 3. That way we just have 1s, 2s, and 3s. It's fine to take a 3 as long as you've taken a 1 first. But I'm wondering if, like, maybe it's possible to reduce this array, this list a little bit. Does it still work right now? It's kind of surprising. We could probably simplify this too. Let's console log stones, sum, and term. See what I missed. I think it's always one person's turn, no? What's the deal with that? What is going on? Why is it never changing turns? Oh my goodness. There's no way that's... Oh my gosh. It's always on the bind now. That's kind of crazy. What is going on? Turn is true, but the turn is still true. Oh my gosh. Alright, do we still get to test 34? Or 32, I guess. Okay, after this, we could simplify it even further. Okay, I see a way to simplify even further. I should have done this. Yes. And now it just becomes a game of reduce total value, total sub value plus plus, and then the input is 0, 0, 0, 0. And then return total. We'll run this. Cool. So we could just make it a map. Run it for a few test cases. Like that. Cool. And then here we could say stones 0, and not stone sub 1, and not stones sub 2. And then here we could do for let I equals 1, I is less than or equal to 3, I plus plus. And then we could say if stone plus sum mod 3 equals 0 something else something. I think it's just gonna be stone sub I. Might be able to do I think we return Bob by default. No. We need that. I don't think we should ever get here. We'll just do this. Actually, basically, we want to be able to pull a rock that doesn't make us lose. Yeah, we want to find ways to help us survive. If we don't find a way to help us survive, then the opponent has won. But there's definitely going to be a stone because we've checked. We've already checked if there's a stone. There should be stones 1, 2, and 3. So a stone plus I is guaranteed. No, it's not guaranteed. It's gonna be sum plus I. So we're looking at stones sub I to see if it has any more stones of that value. And the sum we will plus I. 3, then we will do dp, excuse me, stones sub I stone sub I -1, and the sum plus I, and then it's not returning 1. Pretty much we want to find a stone that we could take that makes us the winner. If we do, that's the stone we're gonna take, and we're gonna say that we're the winner. That's the idea. We just have some kind of a logic error though. So yeah. So okie dokie, run it. We can get rid of this console log, this extra code. Run that. Excuse me. Excellent. So we want to make sure things are properly decrementing. So stones 1 1 0, nice, and then it should be 0 1 0. The sum is 1, false, nice, and then we take 2, the sum is 3. Take true. And so true found a way out. True found a way to win for this. And then false, return, and this time they process the 2 first, which gives them 2, and then they process the 1, which gives them 3. And found a way out. So we're not hitting this. We always find a way out, but the way out, I feel like we shouldn't be hitting this because we're getting 3. Sum plus I, not 3. Like they really shouldn't want to pull this, but I don't know. I don't know if that's related. Wow. That was related. All right, let's get rid of these logs. Let's run it again. Make sure there's no logs. How many have I solved so far? That is a great question. I will tell you in a moment. Let me just submit this, see if I get success or not. Wow. not a success. I got to the same part. So how many problems have I solved? 25. Measly 25. I only just started maybe a week or two ago. But they've also mostly been easy. I think I've solved half as many mediums as I have I've done easies, and half as many hards as I've done mediums. Yeah. But yeah, before we know it, I'm sure that I'll have done hundreds. This one is a doozy though. I wonder if we can make it more... make it even better? Like, this is probably solvable in N, I feel like. I think at this point... Have you analyzed time complexity for DP before? Well, I would say that the time complexity of this... it's gonna have something to do with the number 3. I will say what I have is a lot better, but yeah, it's still not good enough. I used to have a much more intense loop here. I used to have a much more intense array duplication here. At the very least, we have something a lot better, but in terms of how complex it is, it's probably going to be like pretty much for worst case scenario, it's going to be for every stone cubed, probably n cubed is probably the complexity right now. So every stone that we have, we're gonna run this 3 times. I think I might need an official hint soon. This is a killer. Stones times sum times turn states. I do kind of wonder if, like, I just knew a certain math principle, if that would make it easier. Turn equals dp. Because the thing is, I have like this simplify here. Right? In theory, I feel like there's probably some math equation that you could look at these numbers and determine who the winner's going to be. I think I'm going to have to take a hint. I'm going to have to cave. Spend so much time on this problem. There are limited outcomes given the current sum and the stones remaining. I feel like you said something like that. The idea of like forcing certain moves. We can greedily simulate taking a stone with remainder 1 or 2 divided by 3. I feel like I kind of did that. Dang. This actually doesn't have a high acceptance rate either. So again, I'm curious why it's medium. I feel like you're suggesting that I don't use recursion. So therefore, I might be able to do it with a for loop. I'm suddenly going back to this idea of using a cache. Yeah, I think I need another hint. I don't have enough, I don't have any ideas. This idea was the best idea that I've had so far in terms of solving this problem. Can we greedily simulate starting with taking a stone, the remainder 1, 2. Okay, let's try that. How can we do greed? There's a limited outcome given the current sum and the stones remaining. Can we greedily simulate? Starting with taking a stone with remainder 1 or 2 divided by 3. Just take the first stone. I suppose we will make another attempt at it and make some kind of a greedy algorithm. Length equals stones dot length. For let I equals 0, I is less than stones dot length I plus plus. Length. I guess this would be let, and this will be while length. Turn Bob. Let turn equal Alice. Turn equals not turn. And then we have to do sum. If sum sub I, sum plus stone sub I, we'll do stone as a variable in here. If sum plus stone is mod 3 equals is not equal to 0, then we'll remove it, otherwise, and we'll break. And then I guess there's the question of, what if we reach the end of the for loop? We'll create this variable. If they didn't pick, we'll return turn. Length minus minus. And then we'll say stone sub I equals stone sub length minus 1. Length minus minus, picked equals true. I'll run that. I didn't do sum plus equals stone. Run it. Okay. Do a log here. Bob. Did not pick. Do a console log here of some turn length. Let's also, I guess, print stones. I'll do that. I don't like breaks. Picked. Stone. Run it. The order of operations. Okay. Is it good enough? I don't know why, it just doesn't feel like it would be good enough. My next idea is to do equals stones dot map stone mod 3 or 3 dot sort. Basically, the idea being to take the lowest numbers first. Alright, submit it. I did get further. but it doesn't work. I feel like if I could just think about what the... I feel like it's just like a really complex math problem. Picked length, picked stones. Like you have this idea, I obviously don't want to pick a stone that makes you lose, but you also don't want to pick a stone so that the next turn you definitely lose. So you gotta pick stones in a way so that there's always a way out of a bad scenario. So I do think like this is important. I do const 1, 2, 3. Let we do dot for each. Remainder. I'll just do a switch, I guess. All right, I like that. One, 2, 3. We don't do this anymore. It's a doozy. We'll do this for now. Just want to make sure we actually exit the loop. That's the main thing. I want to make sure we exited the loop. And then I feel like we just need to add extra conditions. Gonna run it again just to make sure we're exiting. Great. And then there's so basically I'll only take there's nothing to take, then return not thing. I'll only take a 1 if there's more than 1, or I'll take a 1 if there's more than 1, or if there's a 3. That seems wrong. I guess it kind of depends on what the current sum is. I'll only take a 2 if there's a 1 or a 3. Ooh. I think I'm getting to the point where I just need to see the solution and then solve a similar problem with that solution. Because I think I'm just coming up with worse and worse answers now. Yeah, I think it's time. Maybe I could look at it in a different language. Big O N? You could do big O N. Alice starts with mod 3 equals 1. Alice and Bob have to pick in order. Alice starts with mod 3 equal 2. Alice and Bob have to pick 2, 2, 1, 2, 1 in order. If Alice starts with 1, then Alice needs 1. And Bob needs 2. If 1 is much more than 2, then Bob is going to lose. So if counts of 0 equals 0, so consider the number of multiples of 3. If count 0 is even, Bob picks 3. To pick another, the result won't be affected. If count is odd, the result will be reversed. I mean, that's cool that it's a big O and, but it's like, it's not intuitive. So count is 3 and A is stones. I mean, they did something that I thought to do. If this is Lee 215, his are kind of hard to understand for beginner. Damn, I'm a beginner. Math min. Let's see who this is. Yeah, it is Lee. All right. Yeah, I mean, this this really seems like a very complicated math problem. I think ChatGPT is better than all LeetCode posts. Okay, this is quite literally what I did. C1. Oh, I wouldn't say that I was close, but like I knew that summing these was important, and then there was maybe some kind of complicated math problem to solve after that. It seems like that's what they did. They summed all the values, or not summed them, they counted all the values. Then they saw if there's basically no 1s and 2s, then the Alice lost. If there's an even number of 3s, then we need to see if there's many 1s and 2s. Because I imagine that if there's an even number of 3s and there's some 0s or some 1s and 2s, then you can like take a 1 or a 2, and then at that point you could just keep taking 3s and they'll eventually cancel each other out. But these both need to be greater than 0 for Alice to be the winner. ones and twos, if the difference between the ones and twos, it's just, yeah. Big ON is the best you could do. I had some sense of that, but I'm not gonna put a solution here because it doesn't feel honest. It's an interesting problem. Thanks for sharing it, Chris. I don't know if you have any others. That one was a doozy. See, in my opinion, I feel like that one should have been hard, and it's not like that it's... Once you know the reasoning, it's not hard to write, but to figure out the reasoning, the logic, to simplify it is hard. So to me, this is hard. Bye. Are there like, is this like a daily challenge? What does this mean? That's a good medium though. I do want to see if I can find a hard. Like I did something like this already, wildcard matching. I don't know why I don't want to do integer to Roman. I did try threesome before. I did look up, maybe I'll try it. I did try before, and I couldn't do better than like n cubed, but I did look up a solution that was explained using words, not code. So maybe I can attempt to see if I truly understood it, because I think that's the most important thing, is actually understanding the solutions. So I think we need to keep track of the result. And then we do for let I equals 0, I is less than num.length, I plus plus. And we need to sort it first. Because we're going to use a greedy algorithm to solve it. And then we have to say let left equal I plus 1 and right equal nums dot length minus 1. And then something like while left is not equal to right. Yeah, not equals. And then we'll do const sum equals num sub I plus num sub left plus num sub right. If sum equals 0, result dot push an array with num sub I, nums sub left, nums sub right. Excellent. And then if we do find a match, we need to say, we need to do left plus plus and right plus minus minus. And we also need to start skipping things, so we gotta do while. Actually, we could probably do it later. There's no point of processing something we've already done. So we could do while left num sub left equals num sub left minus 1. Left plus plus. So basically, if we've already tried this sum, we're just gonna skip it. And we need to do something similar for the right. Except it's all opposite. And we need to do a little bit more. We need to do else if sum is less than 0. So if sum is less than 0, that means that we just don't have enough of a value, which means since it's sorted, we need to bring the leftover one to increase our sum. Otherwise, we need to change our right. Something like that. Well, apparently we ran out of time. We'll do less than. Just yeah, less than, because they could be right next to each other and then switch because of this. And then it just runs forever. Let's log a little bit. Oh. Right, minus minus. Alright, what's the issue? That we have a duplicate. In theory, this was supposed to help prevent duplicates. I'll do a console log of nums as well. Num sub left equals num sub left minus 1. Then we go left. Remove the left pointer. Num sub right equals num sub right plus 1. So we'll get rid of this, we'll run it. Okay, so -1, -0, 1. We'll have -0, 1 and -0, 1. So these actually need to come first. And last? Let's just try this. I think we would kind of get like an out of bounds issue. Okay, and so this just ends up skipping everything. So I guess we have to do this here as well. No. Okay, I don't think it's num. I think rather than doing this, we need to say I++ here. And then we have to do while I num sub I minus 1 equals num sub I. We'll do more I++s at the end. Right? Okay, submit it. No, wrong answer. Oh my gosh. It's sorting it like strings. Wait, I don't know. Maybe it wasn't. But I was looking at this, not this. Wait, let me try that again. Yeah, it's not sorting it properly. It's like -1 comes before -2. I mean, this is actually correct. But now it's incrementing -2, 3, 4, 5. So yeah, we do need this here. And then we end up with another issue. And we are missing-ish an element. So I got -1, 0, 1, which should be the last thing. So I'm missing -1, -1, 2. So why am I missing -1, -1, 2? Oh, wait, -1, -1, 2. I should have gotten it. Because when I get to here, it should be -1, -1, 3. That'd be -2, +1. Which would... It should bring the right down by 1. Oh my gosh. Okay. My bad. We only do this here. No, but we also do it here. No. It's a lot of code, I will admit, but it works. I wonder if the log hurts us. Okay. Alright, I'm curious what the better solutions look like. I'm glad that I did that because it shows that I did understand the problem solution. Whoa. Oh. They prevent duplicates this way. Oh, so they like avoided the whole while loop thing and instead did this, which is somehow faster. I wouldn't have thought that like creating an array of strings, converting them to a single string would be so fast, but apparently it is. Okay, at any rate, let's see. This seems like the most attempted solution. So you only do this here. You don't have to do it here or here. I guess that. But why wouldn't you do it? Because like, if it is the same, you're just trying the same thing all over again. So what you're telling me is you don't have to do this, you don't have to do this. I mean, they also didn't do this. Why did I have to do that and they didn't? Oh, it's n-2. Why is it n-2? And then the right is... Oh my gosh. That's right. We can't go all the way to the end. We can't even go next to the end. We can't... Interesting. I totally forgot about that aspect. that we're basically going out of bounds with the array. Okay, then I was wondering why. Can we get rid of that? If not, then how did they not need it? How did they get away with not doing that step? Oh, they did it just like this, though. Okay, I think I'm pretty clear on this one. Maybe try this. Alright, letter combination of a phone number. Given a string combining digits 2 to 9 inclusive, return all possible letter combinations of that number could be present. Return the answer in any order. The mapping of digits to letters, just like on telephone, is given below. Note that one does not map to any letters. Okay. So it literally uses the word map, so. We're just going to make a map. Six MNO 7 REQRS 8 TUV 9 WXYZ. So the constraints 1 to 4 digits. Digits are in the range of 2 to 9, and they are strings. So we'll mark these as string. And so I'm gonna add what we have so far, which is nothing, and gonna do const result equals digits. Is it an array? No. Dot split on the empty string, and then we're gonna map it. Lat map it. Digit. And then the idea is mapping sub digit dot lat map letter I guess I have to do this. And then this. And then we'll do return. Do we need to use recursion? I could probably get away without it, right? Yeah. Let's try to do it without it. I think we need to do a reduce though. And return so far dot map so far is so far plus letter. I think that's all. I did not put an equal sign. Do some logging. My guess is that none of this is happening, but we'll see. Okay. We are doing 2, 3, we do A, B, C. Yes. What we need to do is the I think we gotta see if so far dot length. Otherwise it's just gonna be a letter. Something like that. Nice. Now it's just a matter of, is it fast enough? So we'll submit it. It's fast enough, 100%. Let's see what other people's solutions were. And so they also made a map. They had an array of results. They had digits, and they did backtracking, which had an empty string. Oh wow, so they Okay, so they start at the beginning and then they do it recursively. And then once they hit the end of the string, they push the combo. That's really interesting. They also used recursion. And they also had this concept of an array keeping track outside of the recursion. Nice. They use recursion as well. This recursion seemed to be a recurring theme. I was fortunately able to get away with not using recursion. Just using for loops and mappings. So let's pick up another challenge. If anyone has any suggestions, I'll take them. But foursome. I just saw threesome. There's a foursome? Remove nth node from end of list. What does that even mean? How can you be the nth node and the end of the list? Curious. Given the head of a linked list, remove the nth node from the end of the list and return its head. Given the head of a linked list, so this head is the head of a linked list, which is defined like this. Remove the nth node from the end of the list and return its head. I see. Sure. Okay, so in this example, n is 2, 0, 1. Remove the nth node from the list and return its head. So 0, 1, 2, 3, 4. I'm kind of confused why. Okay, so it's not zero based. Wait, what? Is it zero based or not? Remove it, then return. Remove from the end. Okay, okay. I have not been understanding from the end of the list. No wonder I'm not understanding it. It's because it means work your way from the end of the list. So this is the second. So 0, 1, 2. No. 1, 2 from the end of the list. This gets removed and we return its head. Got it. Understanding the question is the most important part. Okay, so let's think about it a little bit. We don't want to... We only have this value and next, so we don't want to convert it to an array, for sure. So how do we go first thought is to go as deep as we can. Yeah, my naive solution push. N is always, could be size. But because n is one based. N is one based. Not a zero base index. I first want to think if there's think of a way to do this in linear space. But nothing's really coming to me, so I'll think while I do this. While head list dot push head equals head dot next. And then it's saying to remove it, so we'll do const end equals list dot at n minus n minus 1. So if n is 0, if n is 1, it becomes 0, and then it'll become minus. Sorry, if n is 1, it'll become minus 1, which should become minus 2. So we'll just do minus n. Right? So this is the thing we want to remove. So the head, so that doesn't even matter. This is the new head. We'll return head, and then we'll say head.next equals head.next. We'll run this and just see if I'm understanding any aspect of what they're suggesting. Okay. We'll do console log list and then head. This will be -1, -2. In the header linked list, remove the nth node, return its head. Output is an empty array, which should just be null, I think. So we gotta do if what if it doesn't have a head? Guess we gotta do that for one. Oh, we gotta do it here too. Okay. If there's no head, return null. Wait, what? That's what it said to return. 1, 2, 4 gets removed, and we return 3, 5. What is it talking about? Yeah, I guess given that test case, it's not very clear. The test case is cleared up for sure, but shouldn't be an empty array. All right, given our new understanding, and so this is if there is. Oh, that's why we return a new head. Because we could have removed the original. All right. They just wanted null. Undefined is not good enough. Okay. I'm curious if we can do this with Big O1 memory though. Okay, well, the best solution did not. This works. I did this. Nice. What do slower solutions look like? Oh wow, so They went through the list twice. They also took up just as much memory, so there's really no point going through array twice if you're going to use the same memory. Okay. Cool. Alright, I think that's it for me. We did quite a few problems, but I think that I'm starting to lose a little bit of fire. So I'm going to take a break from here. Thanks for tuning in, everyone. I'll be on Monday around the same time. Hopefully have some interviews. And if I don't, hopefully they don't. Or if I do, hopefully they don't cancel last second. Yeah, thanks for hanging out. I'll see you next time. Bye.